Hello everyone, welcome back. Today we are diving deep into one of the most critical topic in computer science and software engineering, time complexity and loop analysis. Let's address the elephant in the room. When you write code, it's not just about getting the correct output. Any code can yield the correct output if you give it an infinite amount of time. The real question is how efficiently does your code run as your out input size grows to million or billions. If your code take 10 seconds to run for a small input but takes 10 years when the input size doubles, your system is practically useless. This is why we study time complexity. Today we are going to build a solid foundation here. So let's see our roadmap for today. So first we will tackle the mathematical tool that terrifies many beginners but is actually very simple, logarithm. Then we will look at how logarithms naturally show up in loops through division multiplication operation. We will analyze a very common and dangerous programming trap, the infinite loop error. And finally, we will look at nested loops and learn how to mathematically trace them step by step. And using a bulletproof tool, I can call the table method. Let's start with the math. What is logarithm? If you look at textbook, the definition can feel abstract and intimidating. I want you to remember one simple phrase. A logarithm is simple, the inverse of an exponential function. Let's break down what this actually means. If we have an exponent like b to the power c is equals to a, so here b is base, c is exponent or power, and a is the result. If we want to reverse this operation, meaning we can say we know the base b and we know the result is a, but we want to find out what power c we raise it to. So we use a logarithm log b a is equals to c. In plain in English, when you see log ba, you should ask yourself this exact question: to what power do I need to raise my base b so that I get my target number a? Let's practice this together. I want everyone to answer. Write down log base to 64. Applying our question to what power must be raised to get 64, let's write out our powers of 2 on the side. We can say 2 is to the power 1 is 2, 2 is to the power 2 is 4, and 2 is to the power 3 is 8. Same, 2 is to the power 4 is 16, and 2 is to the power 5 is 32. And 2 is to the power 6 is equals to 16. Correct? Now look at that. 2 is to the power 6 is equals to 64. So log base 264 is simply 6. Easy, right? Let's try the other one. So base 3. Okay, so we can say log base 3 27. So here you can see 3 is to the power 1 is 3, 3 is to the power 2 is 9, and 3 is to the power 3 is equals to 27. So the answer is 3. Correct? And same for the other one, log base 5 to the log base 5 25. So same, 5 to the power 1 is 5 and 5 is to the power 2 is equals to 25. So the answer is 2. Correct? Now we have a mixed question, log base 2, 3 is to the power 5. So we know that 2 to the power 3 is 8 and 2 to the power 4 is 16. So the number lies, we can say 3 to the power is 243. So now we need to find 2 to the power c is equals to 243. So therefore we can say c is something around 7.92. I will give you one more question. Log base to 10. So we know that 2 to the power 3 is 8 and 2 to the power 4 is equals to 16. The number lies 10, right, between 8 and 16, because our question is log base to the power 2 10. Correct? So that means our power c must be somewhere between 3 and 4. It will be a decimal value, roughly 3 something. In programming, we don't deal with fractional loop iteration. A loop can run 3 times or 4 times, but it can never run 3.3 times. So therefore, in time complexity, we always take the floor value. When we get a decimal number, taking a floor means we drop the decimal part completely and take the lower integer. So for log 2 base 2, 10, we say the result is 3. I think it's clear now. If you have any query, please post in the comment section. I will try to answer. So now the next topic is the discrete boundary floor function. So just now I have completed that example, right? Log base to 10. So how we get the value 3. So let's test this concept. What is log base to 15? We know 2 to the power 3 is 8 and 2 to the power 4 is 16. So 15 is extremely close to 16. So mathematically log base to 15 is roughly 3.9. But what is the floor value here? It is still 3. We drop the decimal entirely. This is the crucial rule to remember. Always floor the decimal answer in complexity analysis. Okay. The next is the division by paradigm. How log n is born. We understand logarithms. Let's see how they appear in computer programs. Let me ask you a practical hands-on question. If you have a positive integer n, how many can you divide it by 2 until it reaches 1? Let's trace it manually, okay? Let's say n is 100, okay? If you see, first we divide 100 by 2, we got 50. Again, if we divide, we got 25. And again, divide 25, we got 12 point something, correct? But remember, we do integer division. So we ignore the decimal. So we got the 12, okay? Again, if we divide 12 by 2, we got 6. And again, if you divide, we got 3. And last, if you divide 6th time, you got 1. So we can say it exactly 6 times to go from 100 down to 1. Correct? Let's try again. The other example, or maybe smaller number, 9. So if you divide 9 by 2, you got 4.5 something because it is an integer. So we will take only 4, and again if you divide, we got 2, and again if you divide, we got 1. So in 3 iteration, you got the result. Now let's look at the mathematical pattern behind this process. Okay. So there is some observation. I think you can see here for 109 example. So let's start with our input n and trace what happened mathematically after each division. After first division, our number becomes n divided by 2 to the power 1. Correct? Because if you divide 100 divided by 2 is 50, correct? If in the second division, the number becomes n is to the n divided by 2 to the power 2. Because in the first time you got 50 and 25. So if you divide 100 by 2 to the power 2 means 4, you got 25, correct? Same. If you divide again third division, you got we can say n divided by 2 to the power 3. Again, if you divide 100 by 2 to the power 3, you got something around 12, correct? 12.5 because it is an integer, you got 12, correct? If we continue this process for some arbitrary numbers of steps, say k times, our number will become n divided by 2 to the power k, correct? After k division. As we know, we want to stop dividing when our number finally reaches 1. So let's set this expression is equals to 1. If we multiply both sides by 2 to the power k, we get n is equals to 2 to the power k. So this is beautiful. Okay. Elegant proof. The number of times you need to divide n by 2 to get to 1 is exactly log base to n times. So I think that's clear, right? Okay, let's verify this with our previous example. Okay, n is equals to 100. If you log base to 100, since 2 to the power 6 is 64 and 2 to the power 7 is 28, the value is some 6 something. So taking the floor give us 6. It matches our manual trace perfectly, correct? This means if you see code that look like while I is greater than 1 and under that I is equals to I divided by 2, this always run in order of log n. Okay. So if I start at n and it will divide itself by 2 at each iteration, the number of iteration and therefore the time complexity of this loop is mathematically bounded by order of log n. Go to the next topic. Multiplication by 2. What if we go in the opposite direction. Instead of dividing a large number down to 1, what if we start at 1 and multiply our way to up to n? So for example, we can say we have one for loop which start from I and it will go till n, and value of I is I into 2. Okay. So let's trace the value of I across iteration. So first iteration is I is equals to 1, which is 2 to the power 0. Iteration 2 is I is equals to 2, which is 2 to the power 1. Correct? 2 to the power 1. Then we have 2 to the power 2, and in the fourth one we have 2 to the power 3. The loop, maybe if we go till k, we can say the loop will terminate as soon as I reaches or exceed n. So let's find out the boundary point is 2 to the power k is less than is equals to n. So this means multiplying a value by 2 at each step is simply the reverse part of dividing by 2. It takes the exact same number of steps. If it takes log n steps to climb down the ladder, it will take log n steps to climb back up. Thus, the time complexity of a multiplication by 2 loop is also order of log n. Let's see if we have any question. Let me show you a classic interview question that catches many smart students off guard. What happens if we write this loop instead? We will start, and it will start from I is 0 to I is less than n, and I is equals to I multiplied by 2. So look closely at this loop. What is the starting value of I? It is 0. Let's trace this loop step by step. We start with I is equals to 0, and at the end of the first iteration, we execute the update step. I is equals to I multiply 2. So what is 0 into 2? It is still 0. So in the next iteration, it is I is 0. So we multiply by 2 again and it remains 0. So no matter how many times this loop run, I will never increase. I will stay stuck at 0 forever, because 0 is less than is equals to n, and will always remain true assuming n is greater than is equals to 0. So this code will run forever. It is an infinite loop. This is an incredibly important lesson. Always pay attention to your initialization and boundary conditions. A single misplaced initial value can turn an elegant order of log n algorithm into a proper crashing infinite loop. So I think now it's clear about the infinite zero trap. The next is introduction to nested loop, the table method. So now that we have mastered single loops, let's step up our game. Let's talk about nested loops. Okay. So where we have a loop running inside another loop. A lot of students look at the nested loops and immediately guess, oh, there are two loops, so it must be order of n square. And this is terrible habit that leads to wrong answer in exam and interviews. Today I'm going to teach you a bulletproof systematic technique to calculate iteration, the table method. Let's look a simple nested loop to see how this work. You can see somewhere on your screen quiz. Okay. So please first go to the quiz and answer it. So let's construct a table on the board. We will create three columns I, J. I is the outer loop and J is the range of inner loop. Okay. And the number of iteration is the last one iteration. Iteration means the number of iteration it will travel. Okay. So you know the I started from 1 to 10 and J start from I to N. Okay. Correct. So let's analyze our table. The outer loop variable I goes from 1 to 10. For every single value of I, the inner loop starts at j is equals to 1 and runs until j is less than is equals to n, which means it executes exactly n times. To find the total work done by this entire code block, we simply sum up the iteration in our third column. Total iteration you can see. So here you can see 1, 2, 3. So 1, the j is 1 to n. The total iteration is n. Same for 2. The total iteration is n. So we can say the total iteration should be n plus n plus n plus n till n. So we can say it will run 10 times n plus n plus n till 10 times. So 10n we can say, correct? So in big operations, we always ignore the constant multiplier. Why? Because as n grows to a billion, multiplying it by 10 does not change the rate of growth. Therefore, the time complexity of this code is order n. Let's modify this slightly. Okay, so again, you can see one more quiz on your screen. So please check that quiz and answer it. Okay, give you 5 seconds of time. Please answer it and then we will start with the next question. If you are wrong, don't worry. After this class, you never face this type of issues. Okay, so I think you can see the next question on your screen, correct? So first, you can see I have also updated the table I, J, and iteration, outer variable, inner variable range, and iteration, correct? Outer loop runs n times, correct? Because again, I started from 1 to n and J started from 1 to n. Last time it is 1 to 10, correct? So now the outer loop runs n times. For each iteration, the inner loops still run n times. So we are adding n to itself n times. So last time you remember, right? We like add n till 10 times. So we got the value is 10n because I is running till 10. Now I is running also till n. So we can say n plus n plus n plus n till n times. Okay. So we can say n is to n multiply n is equals to n square. So thus the time complexity here is order of n square, correct? Now again, you can see some quiz on the screen. Answer the quiz first and then. So let's tackle a classic nested loop that frequently appears in efficient sorting algorithm like merge sort or quick sort. Look at the inner loop. The variable j start at 1 and doubles on every step. So next time we have j is equals to j into 2. As we proved in section 4, any loop that start at 1 and doubles up to n will execute exactly log base to n. I think you remember, right? So since the outer loop run exactly n times and the inner loop execute log base to n times, for each of those iteration, our total sum of work is n into log base to n. How it is? We have log base to n till n times. So log base to n plus log base to n plus log base to n. So we can say we got something around n into log base to n. So therefore, the final time complexity of this code block is order of n log n. See how simple this is when you use the table method. It completely removes any guesswork and give you a clear mathematical proof of your code performance. So next time, if you get any this type of question where you have some for loop, maybe nested for loop or something, please use the tabular method. It will solve any question very easily. We have one more quiz. So the next is dependent loops, the arithmetic progression, order of n square. Okay, so here finish today lecture with a highly interesting pattern. What happens when the inner loop's boundary depends on the outer loop's variable? So notice that the inner loop run while j is less than is equals to n. This means the inner loop execution limit changes dynamically on every step. Let's trace this using our table method. Look at this beautiful sequence. Okay, when I is 1, the inner loop run 1 times. When I is 2, the inner loop run 2 times. And when I is 3, the inner loop runs 3 times. This continues all the way to n, where all inner loop runs n times. To find the total work done, we must sum this sequence 1 plus 2 plus 3 plus 4 till n. Does anyone recognize this mathematical series? Yes. This is a classic arithmetic progression AP, the sum of first and natural number given by the formula. I think you remember last time we complete that part, right? N square plus n divided by 2 something. So let's apply our big O rules. We ignore the lower order terms as n grows extremely large, n square grows so much faster than n, so that the n term becomes completely negligible. We ignore the constant coefficient. 1 means 1 by 2 means half. This leaves us with n square. Thus the time complexity of this dependent nested loop is order of n square. Okay, I think now it's clear why it is an order of n square, and maybe it's clear, right? If so, let's wrap it. Learn that a logarithm asks to what power do I raise my base to get my target. We proved why division and multiplication loops naturally runs in order of log n time. We saw the dangers of initializing a multiplication loop with zero, which leads to an infinite loop. And finally, we learned the table method, like systematically breaking down constant linear logarithmic and dependent nested loops without ever guessing. Next time, if you have question, please use table method. This is one of the best method to solve this type of question. So in our next class, we will learn how to look at the constraints of a competitive problem and use these time complexity to decide if our code will pass within the standard 1 second execution limit. Thank you. I will see you in the next session.
8. Code. AI. Powering the future.